comes in waves, and one day you'll just wake up and poof, you understand it. You'll have to work really hard to get to that point. I haven't gotten to that point, but it'll happen one day. All right.
You have a doctorate and you still haven't done it? Imagine me.
But see, to me, that's what makes chemistry so charming. There's always more to learn, right? Wouldn't it be such a sad day if like you knew everything? It's like, well, what is there to life now? You guys don't believe me on that, do you? You guys are so quiet all of a sudden, like there's a lot to life besides. Okay.
Bugs.
Yeah, my dog is so cute right now. I could stare at her all day and she gives me no issues.
Okay, so I'm going to do this before we continue to move on. So see this part where it says E is equal to, where'd you go? E is equal to HC over here over lambda.
I don't see anything. If you're
I don't
trying
see
to show
anything.
You
us-
guys aren't seeing anything?
No, I just see you
Nope.
and those cute babies.
Oh, my
I
puppy
have no
wuppies.
clue.
So now you're telling me that you'd rather see pictures of my dogs than see the chemistry slide,
I
right?
know, those are the babies. Yeah.
Yeah, you don't see the kitty in there. She's all
Oh
bad.
God, yeah. Now I see that crazy face.
Oh yeah, I remember that.
I
Okay,
prefer
so
the other
Tubby's just
one.
like, oh. Okay, so remember how, oh my goodness, I'm doing this again. So remember how we did some calculations using C equals to lambda nu. So nu is frequency, lambda is wavelength, and C is the speed of light. But now we have to talk about the energy of your light. And that's going to be equal to HC over lambda. So before we continue on, after you've seen that whole scribble, let's do a couple of problems here. Okay. You're going to start a new hobby. You don't even need to start a new hobby if you're studying chemistry, because you're always going to be learning chemistry, right? So let's do this. Let's determine the energy and this will be in joules, okay? Let's do gamma rays. So we'll just give you let's say like 5 times 10 to the minus 14th meters. And let's do radio waves. And we'll have it be, we'll just use 5 times 10 to the 3rd meters. Okay, so those are my wavelengths. All right. So what about H and C? So C is the speed of light. And that's in meters per second. Let me give you a whole value. Okay. So it's 3 times 10 to the 8 meters per second. And H, this is called Planck's constant. And you don't need to memorize it. Okay, I'll just give it to you. Because the way I look at it, there are things you can look up, or I can just give you versus making you memorize these constants. Constants should be easy to look up. Okay, so 6.626 times 10 to the minus 34 joule seconds. So all we're going to do is for the gamma rays, we're just going to plug it into our formula. All right. And if we're looking for the energy, so we'll just use this formula as is. Okay. So the energy for my gamma rays is going to be equal to 6.626 times 10 to the minus 34 joule seconds times my speed of light divided by my wavelength. Okay. And you can see with my units, my seconds cancel out, my meters cancel out. So I'm going to have units of joules, which is what I want. And then we just multiply it out. And remember, since we have a lot of scientific notation in here, use your parentheses, okay? So you would say open parentheses 6.626 times 10 to the negative 34. And then you close your parentheses times and then open parentheses 3 times 10 to the 8th. Close your parentheses and then say divided, open parentheses 5 times 10 to the negative 14. Okay. If you use your EXP functionality, then it recognizes your scientific notation. Okay. So you get something like 3 point, well, it's one significant figure. So I'll just say 4. Okay. Times 10 to the minus 12. Now that doesn't seem like a lot of energy, but I just want to remind you, this is for one atom emitting this light. Okay, so this is one very small particle worth. All right, so if you end up having 1 mole of atoms or 1 mole of electrons doing this or photons, then you can see it starts getting much larger and more significant. Okay, now if we do the same thing now for my radio waves, okay, so we're going to use that same formula. Planck's constant times the speed of light. And the only difference will be my wavelength. Now it's going to be 5 kilometers. Okay. Then you would get something. I'm just going to go ahead and calculate it. Do you expect it to be larger or smaller than the purple one? The value for my energy.
Smaller?
Mm-hmm. Why is that?
There was only 2 guesses, so I took my chances.
Oh my goodness, this honesty is really getting to me here. Remember we said the longer the wavelength, the lower the energy, right? So I went from really, really small at the gamma rays to really, really large for radio waves. So the amount of energy for my radio waves is much, much smaller. Okay. Make sense? You guys are so quiet all of a sudden. Are you copying this down or are you just trying to think whether it makes sense? Okay, I'm going to just go ahead.
I have a question. When you stopped doing the top equation and you got the 4 times 10 to the negative 12, what did you do to get the radio equation?
That's the same equation, but
Uh-huh.
now I'm using the radio wavelength. So the only difference, this is the same, that's the same equation. So the top 2 numbers are exactly the same. The only difference is the bottom number here. Did you get a different value?
No. I was just I was just writing all my notes down.
Yeah, it's exactly the same, but you just change the wavelength.
Okay.
Okay. So
you.
here's the thing though. I mean, have you ever seen highly energetic type A people? And when you make them sit down, they're constantly moving and tapping and stuff. It's almost like they have a high frequency because they're tapping the table really fast all the time. That's like a high energy gamma ray, right? They're always moving, high energy. And then if you take, you know, someone with low energy, like my dog, if he sits down there,
You probably
Okay,
start recording again.
Yeah, she's
Okay, yeah,
back
yeah.
and it's
Okay.
recording again.
I'm back and it's recording again. And obviously my internet connector supplier does not like my analogy. So I guess I'll stop the analogy. But whenever you see highly relaxed people versus highly anxious people, you'll see anxious people are high energy and they're always moving around like they have a high frequency. Okay.
It's called anxiety.
And then you just mentioned the word chemistry and just thought, gamma rays. Okay. So that's a sample calculation. Now let's go back to this PowerPoint. I'll clean it up so you can actually, I'll try to clean it up. Okay. So let's get the eraser here. Now there's a couple things, oops, we wrote on there. Okay. Let me rewrite that. And let me read it out to you and then see if I need to rewrite it on the share screen. So electromagnetic radiation has both wave-like and particle properties. Okay. So, and then radiation can behave like tiny packets, we call them photons, and they're packets of energy. So I hate to do this, but it's all written on. So let me just show you what we are talking about. So there's a famous experiment. It's called the dual slit experiment. Okay. And if I have waves going through my two slits, let me just put that as red. Then when they go through my two slits, they end up fusing around the corners and they become these semicircles. Okay. And what you'll find is that when they intersect here and here, this is what we call destructive interference. Was there are other places where they add together, and when they add together, this is constructive interference. So what does that all mean? What it means is if I have a detector, okay, over here somewhere, and I'm looking at the detector, then you'll see stripes of dark from the destructive interference. So the light waves interfere with each other and cancel each other out. And then lights where it's really bright because they add together. Okay. So if you go to a pond and you drop two rocks so they land at the same time, okay, in the pond, you'll see that kind of pattern, right? Where they interfere with each other and then they add together. Have you ever done that? Is there a pond nearby that's still water that you can toss a couple of rocks
Yes.
in? And then, okay. Okay, good. All right. Another way you can think about it is that if you're in a bathtub, or probably if you have little kids, or when my little kids were little, no longer big kids, then you put your little kid in here. Okay. That's a big bathtub. And you put water. And I don't know why it is, but a favorite pastime is that if the child slides back and forth in times of just right, they can splash the water out of the tub. Have you ever seen that?
Like a tsunami.
Like a tsunami, I know. And they're laughing and giggling all at the same time because they think it's the funniest thing to try to empty the tub without going through the drain, right? So if they time it back and forth, like a tsunami, they start making the waves go higher and higher. The wave that goes really high, that's like constructive interference. And when they're timing it, they're trying to get it so they're adding to that rhythm. Now, if as I'm worried about, do you guys still see the screen? I'm just trying to get back to the screen. Okay. So when I'm worried about the water splashing out, if I actually put my hand in and go the opposite way as they move forward and I move my hand backwards, I am doing destructive interference. So I'm trying to subtract out that wave to make it flat so they don't splash water and get my floor soaking and everyone falls to the second floor. Okay, does that make sense? Uh-oh.
Yes, it does.
Okay. I'm just like, did it die again? Or you guys are thinking, how can you prevent your kids from soaking the bathroom floor? Okay, so that's destructive and constructive interference. So that is actually what light will typically do. It acts like a wave. So what's this whole thing about light also having particle properties? Well, it turns out if I do this dual slit experiment, I said, well, I'm just curious. What happens if I put my eye right here and try to see what's going on? Okay. Suddenly, all my light doesn't make those waves anymore. You get one bright spot here. You tell the bright spot, and one bright spot there, and everything else is dark. So by putting my eye there to see what's going on and see whether or not they act like particles, they act like particles. Okay, and it's 50-50. If I close my eye, okay, then what happens is that it'll give me that pattern like a wave again. So now, how does this happen? So what happens is this: light doesn't alternate between a particle and a wave because it feels like it. It acts like both at the same time. And the only reason we can see the difference is because we happen to set up the experiment that way. So if I set up my experiment to see if light acts like a particle, I'll see it acting like a particle. If I set up my experiment to see if it acts like a wave, it'll act like a wave. And so that's actually called the wave particle duality. Okay. Makes sense?
Yes.
Okay. All right. Now, when it acts like a particle, these particles actually have no mass. These are massless, and they only have energy, massless packets of energy. And we call these photons. So when we did our calculations, remember, right, we did the E equals HC over lambda. Okay. So right now, when we talk about lambda, we're thinking of light as a wave, the energy of a wave, okay? But it also can be that small amount that we calculated for the energy, that could be for a single photon, okay? So if I shoot out a single photon, it will have a specific wavelength associated with it, and it has a specific energy associated with it. Okay, and that's where light acts like a particle. Okay, and it's kind of like if you don't mind one more analogy before I move on to the next slide. I hate to say this, but it's kind of like my kids when they were younger, and that is when you get a babysitter, and then, or they go to my parents, and then my parents are like, oh, they're so sweet. They say thank you and please. Oh, absolutely. Actually, I was just going to say that my kids will say thank you and please when they're at my parents. And they're both very, very polite. Okay. This one is what you wanted?
No, the last one.
Okay. So when my kids used to go to my parents, they would be super polite, and my parents would tell me just how wonderful they are. And then when they come home, it's completely different. They're not different kids, although I think they're different kids. They're not different kids. They're the same kid, but they have a duality there. Okay. So I hope that made sense what I said.
I understand that very well.
When they're welcome anytime. It's like, you want to keep them permanently? So that kind of thing. Okay, so let me see. Are you seeing the PowerPoint?
Yes.
Yes.
That's interesting. Okay. That's a good thing. That's a good thing. All right. So if I scribble on it, oops. Okay, you see scribbles?
Yeah.
Okay. All right, so let's take a look at the Bohr atom. So here's the thing. We know about light, but what's interesting is this. When you heat up elements, they begin to emit light. All right. So when you look, do you guys have electric burners?
No gas.
Gas. Have you ever seen an electric burner?
Yeah, I've had one in the apartments where I used to live.
Okay. So when you heat it up,
Oh.
doesn't it start glowing red?
Yeah.
Yes.
Okay. So why does it mean that when I apply a voltage across the burner, why is it suddenly emitting red light?
Well, I
Does
thought
not?
it's just to tell us that it's on, so we don't burn ourselves.
No.
Or red
Have you ever like
red means
watched,
heat?
huh?
Does red mean heat?
Well, white
Okay,
also
better.
means heat too. If your Bunsen burn or your burner was glowing white, that's a lot hotter than a red burner,
Yeah,
right?
I would see that. Yeah.
Okay, but my question for you is why would it even glow colors at all?
For safety reasons.
Oh,
Well, that's
really?
what I mean. So it lets us know that it's on, right?
Don't
I don't
touch it.
think,
It's telling you.
uh-huh.
Oh my
I
God.
don't
Never
think
mind.
do you think like your metal rod would say, oh, I have to worry about people around me so they don't get burned?
Isn't it because like the metal is reacting with the heat?
Something's going on, isn't it? Right? The valence electrons are getting
Oh.
excited. Ho, ho, ho. There's some excitement going on. Okay. So here's the thing. When we're looking at these solids that when we describe metals, we don't say, oh yeah, they radiate light. A metal at room temperature, it has this metallic luster, but it doesn't radiate light. Okay. Or a neon light. Exactly, Tyler. A neon light. If you have a neon light bulb off, have you ever looked at it? It's just like this clear glass, right? And then after you plug it in, it buzzes for a second, and then suddenly you get this really gorgeous light. I love neon lights. Okay. So what is happening? And that's where we have to start talking about the electrons, because it has to do with the electrons getting excited. Okay. So when we heat it, like even the burner, electrons in the metals are getting excited to the point that you start seeing red light. Okay. So when we do this, it turns out that whenever we heat up our elements, they will emit light, but they don't emit light in terms of the rainbow. So remember the rainbow that we had there? Okay, see how it's continuous, all the colors, they kind of bleed into each other as they're changing colors? Well, look at this. That doesn't happen here. We just have 4 distinct colors. This is hydrogen. Okay, so when you light up hydrogen, you just get 4 distinct colors. all right, that for the visible light that we can see. And it turns out each element has a different spectrum. Now, when you see this, this is called an emission spectrum. Okay, so now we have to figure out, why does this happen? Well, it's not from the nucleus. We already know about the nucleus with the neutrons and protons. So it has to do with the electrons. Okay. So what Bohr did was,
What was that thing called? The light spectrum?
this was an emission spectrum.
Emission spectrum. Thank you.
Now, astronomers, just so you know, don't usually look at emission spectra. They look at absorption spectra. So I'll tell you what the difference is there. Okay. So this is what Niels Bohr, when he was trying to explain hydrogen, the emission spectrum of hydrogen was, why the distinct lines. And he suggested that, like the solar system, what would happen is that if you have the nucleus like where the sun is, then the electrons might be like where the planets are. They would have specific orbits. Okay, so they would be here, this would be like Mercury, and this would be like Venus. Okay, but what happens is you don't have electrons in between. They're not just anywhere willy-nilly. It would have to be in one of the orbits. Okay. And how does that explain what he sees? Well, the way he explains it then is this. If, as Tyler suggests, I put in energy and my electron comes here and it jumps into another orbit, okay, then what will happen is that when it relaxes, it will go down, but it can't go anywhere. It has to go down into a specific orbit. Okay, or if it goes all the way down here. So we can only have this energy difference or this energy difference, but nowhere in between. And with that, we now what we call quantized our energy. We have specific units of energy, quanta, versus it can be anything. Okay, so that's how he explained how you had your emission spectrum. So basically, if you look at your emission spectrum, this could be, oh, I went from orbit like from Jupiter to Venus, okay? And this could be, oh, this blue one could be like going from, oh, let's say Saturn to Venus, okay? But you don't find anything going in between. And that's how we can handle and explain quantization of the energies and the emission spectrum. Okay.
Professor,
Yeah.
on the Labster, we had to burn the different elements, and it
Yes.
was giving us different colors. Do you really do that in the lab?
Yes. Yes, we do.
Oh, that would have been fun to do.
It is, the flame test is so much fun. You just like get these sticks that have been soaked in all these different salts and you just burn them. And then we give you knowns and you burn all of them and write down what you see. And then we give you unknowns and you tell me how that works. And Aurora Borealis, I think that's how it works, but I'm not sure. So besides frizzy hair, Tyler, I'm gonna have to look that up. What was that?
I did the flame experiment in high school my junior year, and it was so much fun.
It was so much fun. It really is a lot of fun. And we actually have spectroscopes, so you can actually like look through the spectroscope, and as you're burning, you can see the emission spectrum.
Yeah,
we
that
have
sounds
these
really
little,
fun.
it is really fun. It is so much fun. So this is what we tried, but don't make a smoke bomb pumpkin because set off our fire alarm. I'm so
Oh, is that
sorry.
what you did?
Yeah, but you can actually take a pumpkin. So when I say the Chem Club was burning pumpkins, we made a smoke bomb pumpkin for fun, and that wasn't good. So when you burn pumpkins, what we normally like to do is you can use a little bit of the cupric sulfate, the The copper 2 sulfate that you can buy from like Lowe's or Home Depot, we use it actually to kill plants. So please make sure you don't expose a lot of people. Don't eat it, right? But you can actually use hand sanitizer and coat the inside of your pumpkin and a little bit on the outside. And then if you put some cupric sulfate in and you burn it, it will get this occasional flashes of the green from the copper. Because when you burn copper salts, it turns green. So if you ever buy those fancy compressed wood shaving logs that say, oh, we have color. So what they do is when they make those logs, they also incorporate a lot of different types of salt. So usually they incorporate copper salts in there. And so when you put it in the fireplace, it has this really pretty green color. And it's mixed with, and then like sodium, if you put table salt in there, there's a lot of sodium in pumpkin anyway. So that's why you see more of a very brilliant yellowish color. If you burn borax, and I hadn't tried this, but I'm told if you burn borax, it glows red. So, yes, I'm sorry, Laura. On the last slide, there. Oh, hold on, there.
No, go forward.
Go forward.
There.
There?
We go.
Okay. Okay, so yes, we do flame tests. And that's exactly what we're talking about. With the flame test, the reason that they have these different colors is the heat excites our electrons, okay? And then when they relax, they emit light. And that color is associated with the difference in the energy when my electron goes back down, okay, and relaxes. All right. So let's talk about excitation. And I could draw on that. I love that one. Okay. So excitation and relaxation. So when I have energy come in, so I'm going to put my electron in the ground state here. So when it's in the lowest energy state, this is called the ground state. Okay. Now, since I'm only looking at hydrogen right now, you're going to see it in this orbit. If I look at something like lithium, then all of these would be in the ground state. So it's the lowest energy state for that electron. Okay. It says the ground state. Now, when it absorbs energy, okay, then it undergoes excitation. So excitation, it absorbed energy. Okay. And then what it does, it moves to a higher energy orbit. Okay. And then what will happen is it doesn't, if you think about a particle, like the planets, you're expected to move. It doesn't have to, but I'm only moving it because I need space. So here, this is in the excited state. And what will happen is it does what we call, it relaxes, okay? So when it drops to a lower energy state, this is called relaxation. Dropping to a lower energy state. But if I'm at a high energy state and I'm dropping to a low energy state, that means I have energy I need to get rid of. So that energy comes off as light. So when my electron relaxes, it emits light equal to the difference in energy between my orbits. And that's when it relaxes down to my other orbit. So far, so good?
Yes.
I kind of have no idea what you just said, but I'm doing my best.
Can you
Okay.
repeat it one more time, just slower?
Yeah. Absolutely. I must be in the excited state. Okay, so I'm going to erase this and just oh, you are going to have to follow my highlighter. How's that sound? Here's my electron. See the yellow? Okay, it absorbs energy. So it's excited. That's the process of absorbing energy is called excitation. Okay. So it moves up to a high energy orbit. Okay. Over time, it's going to relax. And when it relaxes, it moves back down to a low energy orbit. Now, it doesn't have to go all the way down to from where it started. It can do it in a few steps. But when it relaxes, it has to get rid of that excess energy. So it emits that energy as light.
You said as light?
Uh-huh.
Okay.
Well, it gets excited by getting lit, by absorbing the energy. So, so there are a few ways you can think about it if I can use an analogy, if you don't mind. That is, suppose you're in your low energy state, okay? And you need to get ready for class. So if you're in a low energy state, you're in the ground state, you need to get ready for class. So you drink a Red Bull. And when you drink the Red Bull, you're full of caffeine, you're full of sugar, and you're very excited. That makes sense?
Better.
Better. Okay.
Okay, so
Yes.
it's excitation, and that's the process of absorbing energy
And then going to a high energy state. Mhm,
on a high energy state. Okay.
mhm. And then if we take that analogy further with the Red Bull, I've never drunk it, but I have had friends that have done that. And what do? By the end of the afternoon, they crash, right?
Mhm.
All that sugar. So when they crash and they go, oh, I got to go home and relax. What are they doing? They're going back into their low energy state. They could do it in one step. They just go home and crash on the sofa. Or they can go and, to the bookstore and then go home. But anyway, when they crash and go back into a lower energy state, that's relaxation. Okay. And in order to do this for the electron, it has to get rid of that excess energy. It emits it as light. Does that help?
Do your friends glow after they drink Red Bull?
Well, I guess men perspire, women glow. So the answer is yeah. But if that means glow in the dark, no. It could be interesting to see, but I never try to here, let me just shove you in the dark room to see if you're glowing. Okay, does that make more sense now how you see it?
Do they always jump to the farthest away possible orbit when excited? And
Nope.
do we need to know anything about those different circles?
Yeah, but here's the thing. You don't need to know how far they jump and how far they go down this semester. But when you take 120 next semester, you'll get to measure it.
Great. In this context, don't need to know. I got it.
Okay. I'm not going to say, did it go from n equals 3 to n equals 2, or did it go from n equals 3 to n equals 1? So you don't need to know that. Okay, I'll teach that to you soon enough in 120. So now, let me see if I can do this.
So just to be clear, the first circle around the electron is the excitation one?
Okay, so if it moves up, that's excitation. So if you're saying this arrow here, saying it moved up, that's excitation.
Wait,
Okay.
You cut out when you said this something moves up.
Yeah, when my circle moves up to a high energy orbit, because it's farther away from my nucleus,
Mhm.
that's excitation. When it goes back down closer to my nucleus, that's relaxation.
Okay.
Did that answer your question?
Yes. When it moves up,
Okay.
that's excitation when it moves up.
Yes. I hope you can see this. I'm
And
not
then
really good at drawing.
when it moves down, that's relaxation.
That's right. And when it relaxes, that's when it emits light.
Okay, that makes sense. Thank you.
You're welcome. So if I had a cow that's in this orbit that's closest to the nucleus, what do you think it becomes?
Did you say a cow?
Yes, if you had a cow
It's
in
giving
this
like
low
Pikachu.
energy orbit. Red Pikachu, because I can't draw. It actually becomes hamburger. You know why? Because it's in the ground state.
I knew a pun was coming.
Oh, I
knew it.
haven't given you one for ages. You knew I had to give you one. Okay. So let me just go back. When you guys see something like this, where it's absorbing energy and going into the excited state, how many of you are astronomers? We don't all jump at once.
No, not me.
Okay, so the way it works for astronomy is when they look at their spectrum, they have the rainbow and then they see dark lines. Okay, so the rainbow's in the background and the dark lines are, this would be called an absorption spectrum. Okay, so it's like the mirror, almost like the opposite image of the emission spectrum. We always focus on the emission spectrum. What's interesting, in my opinion, is this. You know what? On Friday nights and Saturday nights, chemists used to have nothing better to do than to burn things. So we would burn things and run it through a diffraction grating. That's how we saw that emission spectrums are unique per element. Okay. Isn't that cool? And that's actually, and then the astronomers found helium because when they turned their telescopes to the sun and then ran the image through their diffraction grating before they examined it, they had all these dark lines so they could tell what was hydrogen, but they found lines that they couldn't match with anything they knew that was on Earth. Now we know there is a huge pocket out in the desert of California that's the largest reservoir of helium. When that's gone, we don't have any more helium on Earth. But that's why they call it helium, for Helios, the sun. And that's not a pun, that's actually real.
Professor,
Yeah.
can helium be made, or it's once it's done, it's done? Because don't they use it for like MRI machines and stuff like that?
Yes, they do. And when we were running low on helium, and I think we were still running low on helium, but we
Yeah.
don't talk about it anymore. Yeah, then all the MRI machines won't have anything to work with. We can't really make it cost effectively, right? Because then you'd have to do nuclear fusion with hydrogen, and that's very expensive to do. So once it's gone, it really is pretty much gone.
That won't be in our lifetime though, right? No.
No, but then I don't get a lot of helium balloons anymore.
Yeah, for sure.
Okay. No, but you're right. I don't think they anticipate it'll happen in our lifetime, but it's not something that's so far out in the future. So I don't remember how many generations it'll span before we're out of helium. And it's just because helium's so light, it just escapes the atmosphere. Right? So that's part of the reason why we can't get it back. Okay. Did that answer your question?
Yes, thank you.
Yeah, we need to like harvest the sun. I don't know if I want to do that. Then, can you imagine if we start messing around with the sun? That could be bad. Okay, so quantization. So what does it mean to have quantization? That means discrete fixed units. So in other words, we only have an amount of, it's like digitized. So we have the energy from here to here, but we don't have it where it's analog, where we can get any of the energies in between. So that's why Bohr proposed this, okay? And this was really a really important idea, okay? So absorption, okay, when you absorb it, it gets excited, you promote it to a higher energy level. When you emit your energy, that's in the form of light, then it decays and relaxes, and it goes down to a lower energy level. And typically we try to get it to it'll want to go to the ground state, okay? And so
Hey, can you go back for 30 seconds?
for you, Laura, sure. But let me set my timer. I'm kidding. You just tell me when you're ready.
Okay, I'm good.
Okay. Now,
Wait, hold
see.
on.
Oh.
Sorry, Professor. 30 seconds.
Oh, you're holding me holding me to that, huh? Well, it's probably not on your pathway, but for fun, because you guys have nothing better to do, right? You got to take an astronomy class. And your infinite amounts of free time.
This was supposed to be my fun science class, so
Aren't you having fun?
not with this module.
Okay, all done. Thank you.
Okay. So you just need to go to I don't know about the display anymore, but they used to have a display of neon lights at the Science Center and at the Modern Museum of Art. Hold on a second. Daryl, can you let Melodious in? So that sort of thing. Neon lights are just beautiful. Glassworking is gorgeous. All right, now, what about the Bohr atom? So it works really, really well for hydrogen, which is beautiful. We can predict the whole spectrum of hydrogen, both the visible light for IR, for UV. Problem is it breaks down for anything larger than hydrogen. So you get the helium, can't predict it. So the problem, of course, is, do you just say, oh, this is a bad theory or a bad model? And then do we just throw out the baby with the bathwater? And the answer is no, you never throw out the baby with the bathwater. So what does that mean? So what that means is that we have to figure out how to upgrade and improve Bohr's model so we can also explain other elements. Okay, so that's the goal. All right, so one of the
Hey,
things that
and
happens.
Are you
Yes?
going to post this PowerPoint?
Yes, I'm going to have to. And then while I'm doing that, you're going to have to deal with one thing really quick. Let me look at baseball. Not playoff schedule or scores, but baseball analogy to to dating. No, to electrons. Okay, let me see if I can find it. There's a really, I want that picture.
Can you move the slide back while you're searching?
Sure, I'll move the slide back. Okay, so I have one picture down, and let me see if I can find the other one. Okay.
This was like a random thought, but I was looking at like the participants on the Zoom, and I'm like, when we first started, I think it was like 50 students. And
are we
only
down to
Strong has
26
survived.
now? You guys are, yeah. But can I ask you something? Is it making sense? Still, it's a lot of work. I'm not going to tell you that well, I think chemistry is just a lot of hard work. You know what I mean? I won't tell you it's easy.
Heck yes, it is.
I was like, we should all give ourselves a pat on the back because
Pushing through.
we're doing it. Yeah.
You're doing it. You're doing it. So that's good. Okay. Oh, can I find this pitch frequency? Oh, let's see if I can use this.
I agree with Tyler.
Definitely, Tyler.
Wait a second. What did Tyler say?
Professor,
Okay, on
say
that
yes.
note, let's move ahead. Okay. So let's talk about this. All right, so let's talk first about de Broglie. So we know light has wave particle duality, right? Photons versus a wave. So de Broglie proposed maybe all matter has wave particle duality. So he had an equation. He said that, let me just make sure I get this right. Lambda is equal to speed of light divided by the momentum of my object. I just want to make sure I get the units right. No, there's got to be Planck's constant there. Hold on. I think it's HC over MV. That would make more sense. Okay.
What's the C? Oh, okay. I know
Speed
that.
of light, right? So let's see,
Yeah.
joule seconds. So hold on. I just want to make sure I gave you the right formula. Okay, so I'm going to take a look at my unit. So joules is kilograms, meters squared, seconds squared, times meter seconds. Let's see, over kilograms times meter over second. That doesn't look right. Oh, H is times seconds. Okay, so H over. There is no C. Okay. All right, there we go. Sorry, I wanted to make sure I had the formula right for you. Where'd you go? Okay, so why all this? So let me explain why he was doing this. So it turns out if more than light has wave particle duality, then what this equation tells you, if I have a small enough mass and a fast enough, the V, this is V for velocity, okay, a fast enough speed, then we should be able to see wave characteristics, okay? If you took a mass like Superman, he's too heavy, he's too big. So if you calculated what his wavelength would be, it would end up being much, much, much smaller than what we could measure for gamma rays. It would be like 10 to the minus 24. And I was assuming he was 100 kilograms, okay? And then I looked at the speed of a bullet, all right? Too slow, too big. He's only going to look like a particle. However, when you look at electrons, okay, electrons are light enough that they have a tiny mass and they're not even traveling at the speed of light. They're traveling much slower than that, but it's a high enough velocity that when you calculate the wavelength for an electron, it's around X-rays. Okay, so it turns out that electrons have wave particle duality. Okay, so remember that dual slit experiment I told you about that we were using for light? Okay, if I had a beam of electrons and I shot it at my dual slit and I don't have my eyes open, if I look at the screen, it will have the same pattern as you would expect if it were a wave. But now if I say, well, wait a second, how can that be? Let me count my electrons going through. As soon as you start looking at the electrons on the detector, I'll only see a beam of electrons here and a beam of electrons there. So it behaved the same way as light did. Okay, so now we're going to start talking about our electrons as a wave instead of as a particle. And when we do, we're going to be talking about it, and when you hear us talk about them sometimes, we'll talk about them as particles, and other times when we're describing it in the next few slides, we're going to be talking about them as waves, okay? So large objects like Superman, it's negligible, but small objects like an electron, they will have wave-like properties, not wave-like, they are waves. They're both waves and particles at the same time, okay? So now what happens is this. We're trying to figure out what to do about Bohr's model and how to make it so we can describe all the other elements outside of hydrogen. So what Schrodinger did was, if electrons are waves, then he basically tries to just write an equation to describe electrons as waves. Everything we had been doing previously had been looking at electrons as particles. Okay, so when we do that, then this is what happens. So you'll hear this thing called Schrodinger's equation, and you don't really need to know too much about it. I'll just write it up for you just so you go, oh my gosh, what does that mean? So psi is our wave function. So this is Schrodinger's equation. This is how he solves it. Okay, now what happens is if you take the square root of that, okay, that gives you the probability of where your electron is. Okay. So now instead of having orbits where they're like planets orbiting the sun, we now have orbitals, and it's just the probability of finding an electron. So here, what you see is an orbital for the hydrogen atom, and all those little dots, what we've done is we've done calculations, and each time we try another calculation, we find that about 90 to 95% of the time, the electron is within the sphere. Okay, so when you see us draw orbitals, it's not a solid sphere, it's a probability. Okay, so let me just, I hope these are good enough pictures to, I just want to show you these pictures because I think they're worthwhile to see. Okay, so let me show you this first one. All right. So why am I showing you this stuff? So it used to be that if we think of your electron as a particle, then at any point in time, you would think you know where that electron is. Okay, does that make sense? That would be like talking about the orbit. Okay, we would know, oh, the electron's at, here. Oh, if I wait like, half a second, it'll be here. And we can calculate where it is. But that's not the way we think about orbitals. Okay, what we think about an orbital. So excuse this picture, I had a better one. But just look at this spot here for my pitch frequency. So this is what's going to happen. When a pitcher throws the baseball, most of the time it's going to be in this red region. Okay, so the probability is high. And then the probability decreases that goes further out. But here's what happens. 90 to 95% of the time, your baseball is going to be in this region when the pitcher pitches. But sometimes, I can't believe it, but sometimes I've seen the baseball hit the ground before it gets to the batter, or it hits the batter, or the baseball is being thrown to second base, okay, or first base. So there's a probability then, if you're looking at it, that the baseball won't be in this region. It'll be elsewhere, okay? So when we look at orbitals now, it's like looking at this kind of diagram. There's a probability of finding my electron right here, okay? But there is a small percentage of the time where your electron may be elsewhere, okay? Does that make sense? Are you thinking about the Dodgers? Or does this make sense now?
Makes sense in theory. I just don't know why I should care. Oh,
Oh, spoken like Laura.
I mean, I don't mean to be mean. I just
No,
like
no.
this module is just like so hard to
Wrap your head around.
get into. Just like, here's some facts, here's some letters and numbers, get over it. And it's just like, I don't know what's going on.
Yeah, get over it. No, I'm kidding. So we will get to the part, hopefully, where you'll see why it's important. Okay, I hope. Give me a few minutes. The module, believe it or not, is a mix of both hard and easy. If you just say, oh, these are the facts, I just have to memorize these facts and I can get through it, then the answer is yes. We're going through and talking a lot about quantum mechanics, and I got into a long discussion one afternoon with my husband's friend who says, why are you teaching quantum mechanics? It's like, well, we're not really teaching it, but this is where we're talking about the quantum physics, quantum mechanics. Okay, so it's all about probability now. All right. And if you ever decide that you want to get into material science and start thinking about, when we were talking about computers and metalloids and stuff like that, this is all dependent on this stuff. Okay. So that wouldn't happen otherwise. All right. Understanding that this only tells you about 90 to 95% of where your electron is. Now, what happens is this. When we look,
Can you
at
make the
our-
slide bigger? It's in the small.
oh, you're looking at a small one? I'm sorry.
It's okay.
Well, I figure you guys are really young and you have much better eyes than I do, so. Kidding. Well, you're really young and you probably do have much better eyes than I do, but the bottom line is, let me make the big one. Is that better? You see the big one?
Yes, thank you.
Okay, you're welcome. Okay, so what's happening here is this. When you look at your different orbitals now, we don't call them orbits. That's the Bohr model. We call them orbitals. All right. Thank you, Passant, too. What happens is this. The energy levels of each of our different levels, the energy difference gradually decreases. Okay, so n to 1, my nucleus is down here. So this is the lowest energy one. There's an energy level to get to n equals 2. Then that energy decreases to n equals 3, and then to n equals 4. Now, when you look at your principal energy level, okay, you'll hear us oftentimes refer this to the n's or your quantum, your principal quantum number. and you'll hear us talk about shells. Okay, so shell equals 1, shell equals 2, shell equals 3. Part of why we're going through this is you need also, we're going to start talking about the organization within each shell. Okay, and then that's how we figure out what all the compartments are, and then we start putting in our electrons. Okay, so n can be a positive number. It'll start from 1, and believe it or not, practically it can go to very large numbers, to infinity really, but practically it goes from 1 to 7. Okay, and if you look at your periodic table, how many rows do you have in the periodic table?
Isn't it
7.
like 18?
Well, though you're looking at your columns, right?
Oh, yeah, 7.
Oh, 7 rows. And your principal quantum numbers goes from 1 to 7. Okay. So mathematically, if you solve it, you can have 8, but really practically, we don't see 8. We only see n equals 1 through 7. And your periodic table has 7 rows. So now, even though Mendeleev, who made the periodic table, had no idea about quantum mechanics, now we're seeing, oh, even with the quantum mechanics, there's a correlation with what we already know with the periodic table. 7 principal quantum numbers, 7 rows. So now, if you look at the periodic table, how is that organized? And we can now talk about the similarities in their behaviors based on our understanding of how we organize our electrons.
Is that
Okay.
a coincidence or a mistake, or did it get reorganized once everyone figured out the 7-row thing?
No, it's not a coincidence. I mean, it's not, they didn't reorganize it. So the periodic table has been pretty much the same since its inception. And as they discovered more elements, they could just fit in all the blanks. I mean, basically, when Mendeleev published on his periodic table, and then a German scientist within a few months later published the same thing, so he didn't get credited for the periodic table. But there were a lot of gaps. And Mendeleev said, well, we just haven't discovered these elements yet. So this is what I predict. And there were no noble gases that had been discovered at that time. So following the periodic table, there was this huge, I would say, blossoming of people discovering new elements. And when they first discovered a couple new elements, it was actually one of the scientists in the group that discovered a new element said, wait a second, doesn't this sound like what Mendeleev predicted? And sure enough, he predicted the appearance, the density. He predicted more than just, oh, here's the name and the number of protons. He did a lot of predictions, like what the melting point will be. And it correlated really closely when they found the elements. It was silicon, so probably germanium. Okay, and it was germanium, and what was the other one? Now I gotta look at the periodic table, it's right underneath. But basically he predicted it, and that gave credence to the periodic table. And so he wasn't even in existence, I don't believe, when the periodic table and looking at the quantum mechanics describing the electron organization came about. But it just so happens when you solve it, now you can also explain it by understanding our electron orbitals. So it's, I guess you could say it's coincidence, but it's, you know, I think more than happenstance, there is a reason why they corroborate each other. Okay.
That's cool.
It is so
Mendeleev
cool.
was a boss.
Yeah. I mean, I love the part about chemistry where you predict stuff and then you get to see it come true. Okay. So let's talk a little bit more about these principal quantum levels. So in the principal quantum levels, and I'm going to go back to this diagram. I'm sorry, let me erase some stuff to make some space. So I'm not the most organized person in the world, and that's a definite understatement. But this is the way it goes. So when we start talking about the different principal quantum numbers, the different shells, okay, I liken it kind of like to a closet. So in my n=1 shell, there's only one thing you can put in there, okay, and that would be the s orbital. We'll talk about that. But suppose I take my n=2 shell, and then what I can do here is I have enough space to say, well, listen, I can like make an s orbital, and I could put 3 cubbies in here. Those are my p orbitals. And then when n=3, then I can make an s, and then I can have a little cubby here for 3 of them. And then I have 5 little compartments there. Okay. So what's happening is we're trying to figure out all the different compartments that can fit electrons. So when I have my first principal quantum number, the only one I can have in there is my s orbital. And I remember s as like spherical. Okay, so whenever I say s, you're going to think it's spherical in nature. All right. Now, when I have, no, I don't want to fit that in there. Hold on. Let's do principal quantum number 2 first, and then we'll go back and talk about the electrons. I'll do all the orbitals first. Okay. When I have principal quantum level 2, n=2, then I start off with the s just like 1, but now I can put some cubbies in there, and those would be my p orbitals, and I would have 3 of them, px, py, pz. And the way they look, they're like little dumbbells. So if I look at my x, px would be a little dumbbell like this. Py would be a little dumbbell like that. Pz would be a little dumbbell like that. Okay, so I have 3 of them, and that's all 3 together. Okay, now when we talk about a p orbital, these are all the same energy. So, you know, our atoms floating around in our compounds and in our elements don't have this Cartesian coordinate stuck on them. However, this allows us to know how they're oriented with each other. So all of these are 90 degrees from each other. Okay, so even though it has 2 lobes and it's a dumbbell, my electrons can fit in here. Okay, they can be 2 on one side, can be 1 on each, 2 on the other side. The bottom line, this is a probability. So if I say, oh, I have an electron in a p orbital, can it be here? You say, no, it's not in my orbital. Okay. Or you can say, not necessarily no, with that kind of tone, you say, well, I only have a 5% chance or a 10% chance it's right there. Most of the time it's going to be in here. Okay. Now, if I go on to n=3, okay, we have s orbitals, p orbitals, and d orbitals. Okay. So when we have the d orbitals, they look like a clover leaf. So the only one that doesn't look like a clover leaf is actually this one. Okay, everything else has 4 lobes, looks like a clover leaf. And this one actually looks like a dumbbell with a love handle. Okay, so it's like you just grip it here. Now notice they're not touching each other or anything like that. But remember, that's okay, because we're only talking about the probability, right? I mean, it's just like if your friend likes shopping for, you know, I don't know, shoes, then you're not going to find them in a jewelry store, right? They're more likely to be in a shoe store. So those shoe stores might not be connected to each other, but the probability is higher if you're looking for your friend to check out a shoe store. Okay. So, and then the f orbitals. So when n=4, okay, I don't have a picture of them for you. When n=4, then I have S, P, D, and then F. Okay. So this had 2 lobes that had 4. This will have 8 lobes on it. They look like little octopi. So, and notice I only have one. Let me write it out so you don't think I'm talking about one S. Okay. So S's, you only have a single S. You can have up to 3 p orbitals. You can have not up to, but you have 5 d orbitals, and you have 7 f orbitals. Okay. What happens if n equals 5? Well, when n equals 5, you have your S, your P, your D, and your F. But the sad part about n equals 5, you think, well, isn't there like a G or something else? So with 5, we don't get past 5F. We've never had any element that had anything higher than 5F. And when we get to 6, we don't even have anything higher than 6D. And with 7, we have 7S and 7P. So it turns out when I get to my higher principal quantum levels, my higher shells, okay, the only reason we don't have anything higher than F is we just don't have any elements that go that far, okay? Mathematically, they exist, but practically, we haven't seen that, okay? Yes.
So wait, show an orbital. One.
Okay, sorry.
Show me
This
the
one?
clovers or something.
Okay.
So is the center of your graph the nucleus?
Yes.
And these things are zooming around in different shapes, like on a racetrack. Like when you're a little kid and you got cars and there's like the track that you lay. So they're like running around, zooming around in clover shapes.
Well,
am I close?
It's a probability.
So they might be, if they're on this level, they might be zooming around like this.
Yeah, I'll say yes, just because I think I see what you're trying to say. The hard part is you're trying to think of an electron as a particle moving around, right? And sometimes when we describe it, we'll do that. But it's not like I have an electron here bouncing here and here. Okay.
Okay, then what is the point of these shapes?
So in a sense, yes, it is where the electrons are. Okay. The point of these shapes to tell you where the electrons are. But it's not like a particle running around. Here, let's go back. All right.
I always kind of thought of them as satellites, like like the way the planets orbit each other, or
yes,
like, and I thought of it like a satellite moving in a specific direction.
So this is a part that we had the most arguments about. What I was telling you about my husband's friend. So originally, that's what we were talking about. Remember how we talked about the Bohr model, right? I agree with you. It's like, oh, we can see moving around, kind of like planets move around the sun. But then with the quantum mechanics, we no longer talk about it this way. We're just talking about probabilities. And we still fill in electrons and make it look like we have individual particles. So right now, how to put it? Okay, so let me just tell you. Suppose you were supposed to meet up a friend at the mall, okay? And your cell phone dies, the battery dies, and you're running late. So how are you going to find your friend? Because one, you ran late, and two, you can't reach your You can't reach them because your cell phone battery is dead. So when you arrive at the mall, you're going to say, okay, I know what my friend likes. The food court. We're supposed to meet at lunch, but you go to the food court and you don't see your friend there. So then what's the next probable place that you would find your friend?
Still at the parking lot.
Maybe they're still at the parking lot. Okay.
Coffee
So-
shop.
Shoes.
Shoes. Okay. So the bottom line is when you do this analysis, bathroom. Yeah, I'm always doing my bathroom breaks. So when you do your analysis, you're trying to figure out where your friend is most likely to be so you can finally find that person. Does that make sense?
Yeah, I'm with you on the
Okay.
probability of where the person would be.
So when we map that out, exactly, each clover is going to be at a favorite store of an electron. Okay. So if I say, well, what about here? We say, I don't know. I mean, none of the electron doesn't want to be there. It's not in one of the clovers, right? It's not even near one of the clover leaves. Okay. Does that make sense? I mean, you have a 10% chance. I mean, I normally don't tell my friends I'll meet them in the bathroom. So I could look there, but that's that 10% chance, right? Usually I'd say, oh, meet me at the Starbucks or a coffee shop of some sort, or at the food court, or, you know, at the Cheesecake Factory, whatever. You know, I'm always about food. So the bottom line is this. These are our favorite hangouts for the electrons. Okay.
So they're not constantly rotating.
They're not constantly rotating. All we're trying to do is map out hangouts for the electrons.
I just always thought with the little circles that they were moving constantly. So they just like to chill in, they're probably or potentially going to be in a certain place.
Yes. Okay. Now, does it mean they're not moving? Of course it means they're moving. But if I say, oh, it's gonna, I see it's right here. By the time I tell you where it is, it's not there anymore. Okay. But these are the favorite hangouts for your electrons. Okay. So we're not, so right now, when we're talking about these energy levels and the orbitals, we're only trying to tell you, what are my favorite hangouts for the electrons? And then we have to start putting electrons in.
Professor, are you on the energy levels of electrons, the 4 out of 5 screen? Because I don't see anything, but I hear you. Like it sounds like you writing something.
Yeah, the 4 out of 5 screen. That's the one I'm on.
Okay.
I'm just like moving my hands and talking. Okay, so right now, this is just mapping out favorite hangouts. I like that. Favorite hangouts of the electrons. Okay, that's what orbitals are now. Okay. So far, so good. Does that help you? So if you go to the first floor of this mall, the favorite hangout is my s orbital. If you go to the second hangout of the mall, the second floor of the mall, there's an s orbital and some 3 of the p orbitals. Okay. If I go to the third floor, you'll have an s, you'll have 3 p orbitals, and you'll have your d orbitals. Okay. Does that help explain it?
But they're not orbiting.
They're not, then we name them orbitals, but the electrons can be moving, but they're not orbiting. We're not talking about them going in circles around the nucleus.
Or in clover shapes or in what the infinity signs. They're not moving in a predictive way
Yeah.
on each of these floors.
Yeah. I mean, if you're in a store, you know, I can't predict which way you're going to move.
Can you go back one slide?
This one?
No, never mind. Sorry.
What? What was on it that you need me to?
No, I was just trying to see the orbit ones that you were talking about.
Oh, you mean like these? So these are my orbitals, or so here, I'm sorry to do this to you. Okay, so remember how we went through this one? So these are just the shells. So this is like the floor that you're on. Okay. And on the first floor, you only have the S. On the second floor, you have the S and the P. On the third floor, you have S and P and D. Okay. So you have more things on those floors. So right now, all the descriptions that we're doing, okay, is just where things are. We're not telling you how many people are allowed per floor. We're going to do that now, okay? You guys are having a really tough time on this chapter, aren't you?
100%.
Okay. All right.
Yes.
Okay, so kind of bear with me, and then I'll continue to show what happens with the periodic table. So you kind of can see how they correlate, okay? And then we can go from there. But part of it is this. Remember, the electrons, the reason this is important to know is electrons, we're talking about how they behave with light, but we also need to know how they behave because they are responsible for reactions, okay? So if we know where they are and how they behave, that will help us understand reactions, right? I mean, because why does sodium metal, when it becomes a cation, only lose one electron? Okay, so we need to understand that. Now, where I'm going to go after we've talked about this is this one. Oops, go back. Okay. Oh, Pauli exclusion principle. Sorry. All right. So now that you know the s orbital, we have 3 p orbitals, we have 5 d orbitals, and we have 7 f orbitals. So let me tell you how things are organized. So when we talk about n equals 1, n equals 2, right? And I said we talk about these as shells. Okay, there are principal quantum numbers, lots of terms coming out at you. We say these are principal quantum numbers, and we call each one a shell. And in that shell, we have what we call a subshell. And that's where we have S, P, D, and F. And we usually hang around the subshells a lot. And within each subshell, we have orbitals. Okay, so in the S subshell, there's only one s orbital, so they're identical. But in the p subshell, then I can split it apart to say px, py, pz. Okay, the d subshell, I have 5 d orbitals. And you really don't need to know all the nomenclature behind it. Okay, but you're going to have 5 of these. Okay, and then you have 7 f orbitals. Okay, so it's like taking my f subshell and breaking it down. How many things are in there? There's 7 f orbitals. Now, so when we talk about the electrons we're going to be filling in go into the orbital. Okay, so when we talk about it, we're trying to put electrons in our orbitals, and that's why knowing the numbers of orbitals per subshell is important. In each orbital, it can hold a maximum of 2 electrons. Okay, and why is that? So it turns out electrons behave like little magnets. Okay, so if I have a little magnet, let's say this is north and this is south, and I'm putting it into my orbital, the only way I can put another magnet in there is if it's north and south. So we draw little arrows to represent our electrons. Okay, so S can hold 2 electrons. In my P subshell, I have 2, 2, 2. I can hold a maximum of 6. In my D, I have 5 of them. So that means I have a maximum of 10 electrons that can go into my D subshell. And F, I have a maximum of 14. Okay. So the Pauli exclusion principle, that's why we can only draw 2 electrons per orbital. Okay. So now that you know what all our orbitals look like, and now you know where the electrons can go. Okay. So the maximum number of electrons in a 4D sublevel or subshell. Okay. How many D orbitals are there?
Five.
10.
So there are 5 D orbitals in the D subshell. And so the 10 is the maximum number of electrons because each orbital can hold a maximum of 2.
Wait, sorry, Professor, on the
Mhm.
previous slide,
Uh-huh.
is that number always going to be the same?
In terms of how many D orbitals I have?
You know how you put like subshells and then you put S, P, D, F?
Okay, hold on.
Sorry.
No, it's okay. This one?
Yeah, so you see how
Okay.
S is 1, P is 3? Is that number always going to be the same?
Yes. So the
Oh.
number of orbitals in each subshell, that constant. Okay.
Okay.
This is the max number of electrons. Doesn't mean that it will always be the max, but the maximum. Okay, and we'll get
Okay.
to that. Okay.
Okay, makes sense. Thank you.
All right. Sorry, that's the only thing I have difficulty with is trying to fit everything in. Okay. So with the n equals 3 subshell. Sublevel. Okay. So remember in n equals 3, you can have the S, you have P, and you have D, right? Does that make sense? So what's the maximum number of electrons in S?
2,
How many in P?
6,
And how many in D?
10.
So the total number of electrons that I can put in to my shell n equals 3 is equal to what?
18.
Mm-hmm. That interesting?
Could you have 2 510, or does it only increase as you go up?
Oh, no, it'll be 2 610 because we're talking about the maximum. Now, if we're talking about filling in, will you always fill in 6 in the P subshell? No, but we're going to talk about that as soon as I get to that slide about how we fill in electrons. Now that you have the favorite stores, I like that, Tyler. The favorite stores for electrons, so we know where we're going to be looking for them. Now we need to start pairing them up. Okay. We need to put electrons in. So this is what was that?
I just wanted to know, does this is this for only the category n equals 3, or is it just for all n equals whichever? Did I need to rephrase?
No, I think I need. So n equals 2, you're not going to have 18 because n equals 2, you only have S and P. N equals 4, you have S, P, D, and F. So I think,
Oh, okay.
right?
I see what you mean now. That makes sense. Okay.
Okay.
Thank you.
I like the mall analogy, mall floors, stores, right?
Right.
Yeah.
So the
So,
number of stores will be different per floor.
okay. Thank you.
You're welcome. Okay, so let's take a look at the atomic structure. All right, so this is how we fill it up. We go lowest energy to higher energy. Okay. So we fill it first. So you'll hear us talk about this alphabet approach, which means lowest energy first. So how do we do this? Okay, so let's take a look at hydrogen. And when we do this, you can either draw boxes or lines. And usually I just draw a line because it's a little faster. Okay, so what are we doing? So we can make what we call orbital diagrams. An orbital diagram basically tries to use electrons as arrows, okay? And we're just trying to draw what the electrons are doing in their orbital. So if we look at hydrogen, I have one electron, right? I have one proton, therefore one electron. So the way I do, I say, well, what row is hydrogen in? And it's in row 1. And row 1, we know, only has an S. Okay. So now that we know we're in row 1, it only has an S orbital. I have one electron. So we draw an arrow to represent one electron. And that is the orbital diagram for hydrogen. Okay. Now, you'll hear us talk about what we call electronic configuration. And so we can shorthand this. So instead of drawing everything out, you say, well, the first number tells me my principal quantum number. It's 1. The letter tells me the orbital that I'm interested in. That's S. And the superscript right here tells me how many electrons are in that orbital. So the electronic configuration for hydrogen is this. The orbital diagram for hydrogen is this. Okay. All right. Oh my goodness. Let's talk a little bit more. And I normally don't ask you to draw this too much. I might draw it, but I usually don't ask you to draw it too much. So I'm going to use the white space below here. Okay. So if we look at helium, all right, let me just ask you, how many electrons does helium have?
2.
2. Right? 2 protons, 2 electrons. What row is helium in?
In noble gases.
Well,
Row
that's the
1.
column. I agree that it's in the noble gas. That's the column, but it's in row 1, right?
Bottom floor.
The bottom floor. And what is the orbital that's going to be in the bottom floor?
S.
S. Okay. So now my 2 electrons, 1, 2. Right? My electronic configuration is 1s2. Now here's something to note. See this? It's completely full. I can't fit more than 2 electrons in here, right?
Professor, is that a -1L?
Minus 1L.
It's an arrow, up arrow, down arrow.
Up
Oh,
arrow.
okay.
Sorry.
Thank
At some point in my life, I will have better writing. I'm so sorry that you can't read it. Okay. But ask questions. Yes. Up arrow, down arrow. Now let me ask you about lithium. How many electrons does lithium have?
3.
Yes. Okay. Now notice with 3, since helium has 2 and that's full, then to add my third electron, I have to go down to row 2. Okay. So 1, 2, 3. So now the electronic configuration for lithium is 1s2, 2s1.
I thought there was only space for 2 on the S's.
That's right. That's why I had to go down another level. They're not the same S's, right? This is first floor, second floor.
I'm lost, Professor.
So
Okay.
it's S first, S second, and then P is third.
Okay. Hang on.
I don't know if I'm the only one, but
All right. Hold on. So when you look at the first floor, okay, you can only have an S. All right. Then if this is full, you can't shop there. You got to go elsewhere. So you go to the second floor. Now the second floor has S and it has P's. And when you break your S and P's apart, the P's are slightly higher. It's like a ranch house. You have to go up in energy to get to the P's. Okay. When you go to the third floor, let's circle that. When I'm at the third floor, I have S, I have P's, and then I have D's. Okay, so you're lost. This is confusing because all I'm doing is I'm just telling you, this is a structure. This is how we're organizing it. This is how it is organized. Okay. So you say, well, I don't understand it. I hate to say this, this is like, do as I tell you, don't think about it. All right. I know that sounds really rude. I'm not trying to be rude. There's not a lot of understanding if you say, here's your closet, put your dresses over here, put your shirts over here, put your pants over there, and your socks go in the drawer, right? This is how we keep our closet organized, which I don't do, but I should, okay?
And so on level 4, would it be S, P, D, and then F?
Yes,
Okay, kind of like an exponent to the exponent to the exponent.
yeah. And it just turns out I'm going to throw something at you, which you'll probably not like, but that's the way it works. Okay. When you get to floor number 4, it turns out since we have ranch houses, the third part of floor 3 on the ranch house is higher in energy than the 4th floor S, and then higher than the D. Oh, wanted to move this down, is going to be your P's. Okay. So just think of it kind of as a very open store. So you can wander, but when you are in, you know how you have these hospitals that have like different levels and you have a ramp. So basically you're in one building, you're on the 3rd floor, you have S and you go to P, and then suddenly you find yourself in the next building where it says it's floor 4. And then you have to like find your way to get to 3D. So these guys are all part of 3, but it just so happens that energy level wise, 4 is right in between. Okay. Now, in terms of, this is just like looking at a building and the floors and where the closets are. We're just telling you how this building is organized. Okay. And then which is the lowest level, and I've got to do a lot more energy to get to floor 4. I haven't told you how many people we can put in. Now, when we start putting people in, I say, okay, I can only put 2 people in each of these orbitals. So when I have hydrogen, hydrogen only has 1 person, 1 electron. Stays on the first floor. Then helium has 2 people, 2 electrons. I fill up my first floor. So if a third person comes along in lithium, okay, so lithium has, oh, listen, my taxi lithium has 3 people in there. The first 2 go on the first floor. Where's the third person going to go? They can't be on the first floor, so they have to go up to the second floor. Okay. So when beryllium comes along, and that taxi has 4 people, okay? So where do I place all these 4 people? Well, the first 2 that come through the door, I'm going to put an S. And then the third person and fourth person, I can put in and fill in here in the 2S.
Kind of like a quadruple decker bus, and everybody only wants to sit in the first seats or goes in the first seats first.
Yeah, you have them go in the first seats first, and then they're taken. I got to keep moving up, right? Boron.
Like the parking structure, you go and then first level is full, go to the second level.
Yeah. You guys can tell me you're confused and not getting it, because your analogies are exactly spot on. Okay. So I'm not going to listen to that anymore. We'll do boron, and I ran over a minute. So let me do boron. Boron has 5 electrons, right? Because it has 5 protons. So then the first person that comes in goes on the 1S. Second person goes on 1S. Oh my gosh, that parking lot's full. Now I got to drive up to the second level. Go to the second level. Oh, I have 3 more people. So I've used up 3 people, 4 people. Where's my 5th person going to go? Well, they can't go in S. That section's full. So now I have to go into that slightly higher section, not quite the 3rd floor, but you know how they have these ramps that lead you off, and you have to walk farther, and you put the 5th person right here in the P. Okay. Does that make more sense now?
So would that be written as 1S and then with a up arrow, down arrow, 2S, up arrow, down arrow, and then 2P? Or is that a?
Yes. Yes. So when you do your electronic configuration, 1S, I have 2 electrons in there. 2S, I have 2 electrons in there because it's a different floor. So even though it's S, it doesn't matter. It's bigger, different floor. And then this is part of 2P, and I have 1 car in there, or 1 electron in there. Okay.
Just a quick question. So how can you determine how many people can go on each floor? That's the little part I got lost on.
Okay, so the rule is each orbital. Okay, so this is 1 orbital.
Mhm.
Okay, each orbital can have a max of 2 people.
So on
Okay.
level 1, only 2 people can go,
Yes,
and then level 2.
I have a 2, and then 2, 4, 6 is the max. So I would have a maximum of 8 people.
Okay.
And that's
Okay.
how we got the max of 18 for 3.
Okay, that makes sense.
All right.
Mhm.
So now that you're getting this, I'll throw in a few more not modifications, just nuances that you have to be aware of. And then we'll look at our periodic table. So make sure you have a periodic table handy to look at on Tuesday. Is today Tuesday?
Today's Thursday.
Thursday. So Tuesday.
Yes.
I think. I don't know. I forgot about Tuesday. this
No,
week. So
today's definitely Thursday.
Steffi's counting on it. Today's Thursday. Weekend's coming. Okay.
Yes. Please.
All right. So make sure you have your periodic table with you and we'll go through. And once you learn how to do this, then we're going to put you over onto the periodic table. And then for most of the periodic tables, you'll be able to read off of it. Okay.
Prof, we don't have a module listed for next week yet.
Man, I got to put it up for you.
We got nothing. We're at the end of the road.
No, you aren't.
A's for
Don't I
everyone for the
wish?
rest of the
Come on,
rest of
I
the
was
semester.
grading, you know? You
I'll take it.
guys. I'll get your modules done. Okay. That I know that's high priority.
The diagram is very helpful.
Does that mean we're getting more time for this active? We barely learned this today. And
Oh my
seeing how much
goodness,
it's
that was a
helping.
hint if I ever heard one.
Oh,
Let me
just-
get nodules and I'll take a look at it.
Just guess and Google your way through it.
No guessing, no guessing. Come on, you guys. It's gonna
5
be answer
chances,
the
5
periodic
answers. I'm
table.
guessing.
No. You're good. You guys have it. If you're guys telling me, oh, it reminds you of a parking lot, you know, the parking structure. You guys know what
Makes
you're
sense
talking about.
now. It didn't make sense at 4 o'clock in the morning on Sunday.
Well, nothing to me makes sense at 4 o'clock in the morning on a Sunday. So just so you know.
This is, yeah, pretty much. Deadlines.
Yes, I
gotta get this
know,
done.
which I have one. So of many. But anyway, I will then get your modules done and I will see you guys on Tuesday.
Professor,
Yes, Ashley.
I just wanted to let you or remind you that I'm going to the field
Yes, ma'am.
like
I
6,
know.
but I'm working on all my active homework assignments and I should be done with them. So I'll just have the quiz and then I think it would be like 3 labs and
Okay.
of course. So yeah.
Yeah, I'll get
Thank-
them done.
Thanks, Professor. Have a good
No
night.
worries. All right. Good night, everyone.
Good night.
Thanks,
Thank
Prof.
you.
Good night.